Detecting fast RF bursts using log amps. Introduction. Monolithic logarithmic amplifiers, log amps, can handle signals with dynamic ranges up to 100 decibels. They are capable of responding to RF bursts that are as short in duration as a few tenths of nanoseconds. However, when demodulating logarithmic amplifiers are used to detect fast RF bursts, strange tails sometimes appear at the output when the applied burst shuts off. Understanding demodulating logarithmic amplifiers. The first thing to understand about log amps is that while they provide information about power, they actually respond to voltage. In communications technology, the term log amp generally refers to a device that outputs a voltage that is proportional to the logarithm of the envelope of the input signal, scaled to base 10. Another important factor relating to log amps and output tails. Log amps have high sensitivity to very small changes. In amplitude at the low end of their operating range. Figure 1 shows the typical relationship between the input and the output of a log amp. For every 10x increase, 10 per increase in the peak-to-peak voltage at the input, the output increases by 500 millivolts. This is a video about false triggering of FET gates during RF bursts. Here we have as with the oscilloscope. Using logarithmic amplifiers for RF pulse detection. When an RF burst is the input to a demodulating log amp, the output will be a voltage pulse. This can be fed into a comparator to determine the presence or absence of the RF burst, or the amplitude of the RF burst can be determined by measuring the amplitude of the log amp output voltage. Figure 2 shows examples of the strange tails that are sometimes seen at the end of otherwise fast and accurate log amp output voltage pulses. These undesirable tails can cause false readings in radar and other systems where the shape of the detected pulse provides vital information about the target. Figure 2a shows a stationary tail. Figure 2b shows a tail that is jittery, moving up and down the falling edge of the ideal rectangular pulse. Understanding the tail. The tails in these two cases are caused by different mechanisms. The stationary tail in Figure 2a is caused by the pure quality of the RF burst applied to the input of the log amp, while not apparent on the modest voltage and time scales of an oscilloscope. The RF burst does not shut off instantaneously, but instead decays spontaneously. Remember that log amps are highly sensitive to small changes in voltage and at the low end of their dynamic range. Input coupling. The type of jitter shown in Figure 2b is typically the result of improper input fed to the demodulating log amp. Most logarithmic amplifiers are designed to be driven differentially, but most RF signals are ideal signals. This circuit does not convert the single-ended input signal to a differential signal. Instead, the AC component of the RF signals is allowed to pass through to INHI, while INLO sees a low-pass filter version of the signal. Here's another video about an op-amp integrator. Conclusion. The performance of the demodulating log amps need not be hampered by the presence of tails. They occur because of poor quality signal sources or because of the improper selection of component values in the input interface. The most effective solution for the first form of tail is to obtain a better source of burst. The second type of tail can be dealt with using proper interfacing circuits. Techniques include the use of balloons and passive RC circuits, as described here. Active solutions such as single-ended to differential amplifiers are also available to the designer, but they were not covered here. Whatever method is chosen, it is important to keep in mind the issues discussed here.